Did you know that without a special compound, many digestive disorders would remain undiagnosed? This compound is barium sulfate, and today we'll uncover its unique properties and how it is able to be used so effectively in X-ray imaging. Barium sulfate is used for X-rays, particularly in imaging of the digestive system, because of several factors. When ingested orally, it coats the inside of the esophagus, stomach, or intestines, which allows them to be seen more clearly, helping to diagnose certain disorders within the digestive tract. To begin, barium as an element has a high atomic number of 56, which means it has a large number of protons and electrons. High atomic number elements have excellent radiopacities, meaning they are essentially very effective at absorbing X-rays due to their dense electron clouds. In particular, barium extends all the way to the 6s subshell. This occurs because having more electrons results in a higher probability that X-ray photons will interact with them, either through photoelectric absorption or Compton scattering. Similar elements that are used for X-rays include iodine, tungsten, gadolinium, and even gold, which all have high atomic numbers and large radii. Imagine X-rays in this case as beams of light traversing through a dense fog of barium, which blocks and absorbs these X-rays and thus appears white on the X-ray film, providing a clear contrast against the softer tissues that X-rays pass through more easily. That being said, barium ions are highly toxic because they can decrease the level of potassium in the blood, which is crucial for muscle function, including in the heart. As a direct result, this can cause tachycardia, which is increased heart rate, increased or decreased blood pressure, muscle weakness, and even paralysis. On the other hand, barium sulfate is not toxic. One of the main reasons for this is because it is extremely insoluble in water and other liquids. Why? Well, barium sulfate is an ionic compound composed of the barium ion and the sulfate ion. In a crystal lattice, the ions are held together by incredibly strong electrostatic forces of attraction, which is partly due to barium's large radius and 2+ charge. These forces are actually strong enough to surpass the strength of the intermolecular ion dipole forces between the ions and water molecules. As a result, the crystal lattice of barium sulfate remains intact when placed in water, and the compound does not dissolve. This can also be explained in the context of chemical equilibrium. In this case, an equilibrium is established when the rate at which some barium sulfate ions that are breaking away from the solid lattice is exactly matched by the rate at which other ions are returning. This reaction can be represented by the following. Trials have shown that the KSP value for this reaction at 298 Kelvin, or 25 degrees Celsius, is approximately 1.1 times 10 to the negative 10. Given the very low KSP value, the equilibrium position is heavily favored towards the left, which is solid formation, meaning that only a tiny amount of barium ions are released into solution. This small amount is well below toxic levels, ensuring safety for the patient. To further understand this, we can apply Le Chatelier's principle, which explains the fact that even if a small amount of barium sulfate dissolves, the equilibrium will actually shift left to minimize this change, favoring the formation of the solid again. In turn, this means that barium sulfate will not dissolve to any significant extent in the digestive fluids. Remaining in its solid form, which is inert, it will then pass through the digestive tract without releasing the toxic barium ions. In summary, barium sulfate's unique properties make it invaluable in X-ray imaging, providing clear images while ensuring patient safety. Next time you undergo such an X-ray, you'll know the fascinating science keeping you informed and safe.